So again, I'm Dr. Sedat Cevikparmak. I'm the chair and assistant professor of supply chain management here at DeSales University. Started at this position 2 years ago. And so Brennan and I thought this next AI event could be about supply chains because of all the hype that we're hearing about supply chain, right, in the last 2 years. And the past 2 years were quite a challenge for many of us as we all struggled to adapt to the new normal of living with a pandemic. So one area that the pandemic made famous, or maybe should I say notorious, was supply chain management. In retrospect, actually, personally, I think that there was nothing to be surprised about because the past decades, when we look at it, the speed of globalization created a bunch of incredibly complex and stretched out supply chains all over the world for many different businesses, and even for basic products. So as the pandemic started to influence the global trade, supply chains all over the globe were hit hard. But what worsened the situation was, I think, the chaotic nature, length, and timing of the disruptions. The local circumstances we saw dictated how bad the overall global supply chains were being impacted by the pandemic. For example, as the United States was ready to move on from the notorious port congestions in California, some critical ports in China or production facilities in Vietnam were getting hit by restrictions and sending the USA businesses back again to the turmoil. And so again, the chaotic nature, the length, and the timing, because we cannot predict, it was not easy to be prepared, to be resilient. So how do we operate in such an environment? How do we optimize our supply chains so that we are more resilient in the face of those kinds of disruptions? Well, I guess we would all agree that data analytics could help us here. And this is why we have gathered on campus and on Zoom today to hear how a specific notion in data analytics, knowledge graphs, can help us optimize our supply chains. So a team of experts from RelationalAI will share with us their fantastic insights into knowledge graphs and supply chains. And as I was getting ready for this event, I read some readings myself about knowledge graphs, and I can, in my all humbleness, tell you that it's a fascinating tool, very versatile, and it gives an incredible ways of creativity into our data pools. And I'm really excited to hear more about this topic, and I'm hoping that you're all sharing the same sentiment with me. So with that, I'd like to turn the floor back to Brennan to get us started off. Thanks again for joining us.
It's just a minute for me. My name is Brennan Pursell, professor here at DeSales and director of the Center for Data Analytics. Right, it's just kind of common knowledge in this association that we have here with deep learning AI, of what AI is and algorithms that it's based on, the deep learning neural networks that have proven their value to do predictive analytics, prescriptive analytics, image classification, natural language processing, even in association with others, content generation. But knowledge graphs are something different. And knowledge graphs, I'm so excited to hear about this because this is really cutting edge. RelationalAI is a company based in Berkeley, California, correct? But you are distributed remotely throughout the country. They're now on Series B funding. They've raised a total of $122 million, and they are, shall we say, taking us into a different area. And what I think the hope is, and especially the interest here at DeSales University, is what's the use for business, and how can this new technology be applied to help add value to businesses, and especially how can businesses, how can these systems help to answer more intelligent queries of the data, particularly across different formats of data, different data structures, not just the columns and the rows of structural data, structured databases, but maybe across other forms as well. So this is really taking us into a place, the company hasn't really launched onto the marketplace, but they're in development. So I'm really excited to have specialists talk about their emerging technology. So please, Kurt, John, are you anything else?
Sure, yeah.
Okay, here's John Bloys from Relational.
Thank you so much, Brennan. Thank you, Sedat. That was, I had not heard what Sedat you had planned to start with, but it's actually very apropos to some of the work that we've been doing. We call it Knowledge Graphs for Good, but we've been working with the UN to do city resiliency planning and some of the same things that you talk about, the ripple effects in supply chain. How do I model not only what are the immediate effects from a boat going sideways in the Panama Canal, but how do we understand throughout our network and where the stresses are and how can we accommodate those. I'm using this machine here. Which machine am I using?
You're on the right one. Go in the presentation.
Okay, Brennan, just a brief word. So I am in the data analytics business, as are my colleagues, but I'm also Lehigh Valley, born and raised, and I can't tell you enough how impressed I am with the Center for Data Analytics. And I've spoken to you, almost a year ago now, and the vision that you guys had and how you manifested it. I think this is great. I was warned that we would have a mixed audience, that we would have some students, that we would have professors, that we would have supply chain professionals, and we were trying, as we sat and tried to work out our content, we were trying to figure out how do we thread that needle. I got some questions when we were originally saying, hey, knowledge graphs and supply chain optimization. I got some worried LinkedIns that said, I'm really interested in knowledge graphs. I don't know what they are, but if you're going to talk about optimization in detail, is the math going to be over my head? So we tried to make this as not as mathy as possible, but as knowledge graphy as possible. We want you to focus on the value that knowledge graphs can bring in terms of their ability to span across different silos of data, as you mentioned, Brennan, but also the ability to then push knowledge into that graph and use it for reasoning over an enterprise's data. Here's the little bit of math that we've done. My colleagues and I on the way in here, so you'll be hearing from Kurt Stirewalt and Jordan Wright as well. We calculated with our sophisticated math that we, between us, have a little over 75 years of combined enterprise analytic delivery and/or supply chain, direct supply chain experience. And so we hope to use that today to light up some of these examples for you. Because we're going to be trying to accommodate a bunch of different groups, there's going to be some background, there's going to be some specifics. We're going to hopefully make it real for those of you who are interested in seeing the actual product and not just PowerPoint slides. But if I had to upfront tell you what I hope the key takeaways are, first of all, there's a large opportunity to simplify building intelligent data applications at scale, and you do that by consolidating organizational knowledge that is currently siloed in bits of application code throughout an organization. Well, we think knowledge graphs play a key role in this transformation, and they're particularly useful in systems like supply chain, right? So not only are you worried about your own organization's data and the different systems that you work with, sales and inventory and transportation management and so forth, but you have trading partners and you have to integrate with their systems as well. So you have this broad heterogeneous data landscape, and how do you use knowledge graphs to weave those data together and then directly encode knowledge that allows you to automate a bunch of the things that previously were not possible. And we think relational knowledge graphs in particular are going to play a key role in doing that. So this is our agenda. I'll give you a brief but necessary bit of context. I'm going to paint a really broad brush just to give us all sort of a common level of understanding. We'll talk about knowledge silos and the size of the opportunity that we see in the marketplace. We'll talk about relational knowledge graphs, and we'll make it real. Right? So the back half of this, or even more of the back half of this, we'll actually get in to some code, we'll get into the platform, and we will look at what a knowledge graph actually is. Brennan, I thought you did a good job. We are just, as a company, a little bit about us, we're just out of stealth. We're well funded, as may have been mentioned. We've got a bunch of well-known VCs backing us. We've got a very active and accomplished board of directors. We just recently announced Bob Muglia to our board, very passionate about enterprise data, and is the former CEO of Snowflake. If you're familiar with them. They went through a rapid growth phase, and he was in the lead at that point. And then, as you mentioned, we're a 100% remote workforce headquartered in Berkeley. We have almost 140 colleagues, and over a third of them have PhDs, and they're well published, cited something like 100,000 citations. So these are thought leaders in their space, and we also have deep industry experience, companies like Microsoft and IBM and Splunk and Quantum Black and McKinsey and Slalom and so forth. So it is an exciting time to be in the space. So this is how we present what we're doing, right? Stated simply, we're building a next generation database system for building intelligent data apps based on relational knowledge graphs. So there's a lot there, particularly when we have a room full of people who are coming at this from different perspectives. And so when I talk about a brief bit of context, one of the first questions I got when I tried this out on a few people, some who may be in the room, was, well, I don't know what relational is. And then if I know what relational is, relational as opposed to what? So just a quick primer. There's two basic flavors of database systems. There's navigational and there's relational. Navigational was sort of the original enterprise data warehouse back in the 60s. And there's some appealing things to it because it allows you to think of data in terms of, almost in terms of a graph. They were called hierarchical or network databases. And ironically, or interestingly, I guess I should say, one of the earliest implementations of the network database was because it was built specifically because the vendors were having trouble keeping track of the bill of materials for the Saturn V project. It was very detailed, and the sub-assemblies and the sub-sub-assemblies, so it had some value in terms of at least conceptually thinking about how these pieces fit together. The challenge with navigational is that the programmer is essentially the navigator. They have to specify how to access a given record or records via a series of paths and pointers. Relational takes a different approach, and it was fairly rapid at the time that it was introduced in the early 70s, but it became to be the dominant paradigm. And relational is more declarative in nature. You simply say what you want, and the machine optimizes for how to go get it, right? So to give an intuition for some of the students in the room, a navigational approach, I might say, hey, Don, do me a favor, go out to this door, hang a right, make another right, take a third door to the left, walk to the back of the file that's on top of the filing cabinet. That's the record that I'm looking for, right? It's fairly verbose, but it does tell him how to get to that record. The relational approach would just be, grab me any files that look like this, right? It's a lot more compact. It's a lot easier to. It's an easier burden on the programmer, right? It was a different paradigm. It took a while for people to wrap their heads around it, but it became the dominant paradigm. And this is a slide. We won't go into a whole lot of detail, but there's this tension at play. First there was navigational, then there was relational, and we've had some challengers to the relational paradigm over the years, and each time some significant innovation comes along and allows a relational to sort of take the pole position, as it were. And so rather than go into great detail here, I'm going to cut out a few things. This will probably be the most text-dense slide, but I just want to give you a sense for how each of these generations has built off the last. So again, separating the what from the how, this declarative language called structured query language, which some of you are nodding your head, you look like you're familiar with. SQL is almost plain language, like English-like in its structure. It's very simple, right? It's the programming equivalent of, hey, get me files that look like this. And then along with that, there's this notion of a query optimizer. So query optimizer uses relational math and some sophisticated algorithms to take that query and figure out how best to optimize it to go access the data that the programmer was looking for. But one of the benefits of structured query language, or SQL, and being such a plain language expression, is that business analysts could now also work with data, right? And that's continued to this very day. It's 40, 50 years later, and SQL is still kind of the coin of the realm, or the lingua franca in the modern data stack. There was in the aughts and the tens, there was this notion of big data. So we all saw those slides where data was growing exponentially because of devices and the internet and click streams, and not just people but things. You think of the Internet of Things and all the data that they generate and all the read points, and you can follow customer journeys, but product journeys throughout the supply chain. And so it required the exponential growth of data was going like this. The innovations in the original relational databases were sort of on a linear curve. But I would say, 6, 7 years ago, maybe even a little bit longer, BigQuery, Google's BigQuery, Snowflake, and some others had this insight that they would completely redesign the relational paradigm on a cloud-native infrastructure. And what that meant, there was a couple things, and without going into the details too far, they essentially separated the storage from the compute. Storage was immutable, and it lived in buckets in Amazon or cloud stores in Azure. But it did this while it retained all the relational goodness that had value in the early systems. But in addition to that, it was fully managed. It's a cloud-hosted service. You don't have to worry about procuring the machines or the maintenance or hiring DBAs, and you only pay for what you use, right? And there's a bunch of benefits. We won't have time to drill into these today, but essentially, one of the big benefits is just infinite scalability. You can store as much data as you like, and you can use as many CPUs or as few as you need to take care of the job at hand. That's particularly useful in industries, retail and supply chain and retail, where you have a big spike, a seasonal spike, and prior to this, you'd have to buy a bunch of hardware and plan for peak capacity, and then carry the cost of that throughout the rest of the year. You don't have to do that anymore. In fact, this has had such a tremendous impact, and has allowed analysts and others to continue to play a key role in the modern data stack, that Snowflake and BigQuery and Databricks have really become the center of what's called the modern data stack. What we are suggesting is that there's a really good pairing that we see working. We have some innovations on top of Snowflake innovations.
There you go.
Great, thank you. And so we have innovations on top of the relational infrastructure, the cloud-native infrastructure that Snowflake created. We have really fast joins. We have a unique way to sort of store our data in really narrow relations, 1 or 2 column relations. We have, you can think of it as almost like a superset of the query optimizer, a semantic optimizer, that allows you to not only define what data you want, but what logic you want to apply to that data. And we retain all the relational goodness, and we retain all the innovations that the cloud provider have. And that ability to declare logic relationally and execute that way is going to be a big part of how we address what we're going to talk about next, which is knowledge silos. Right? So knowledge silos we see as literally a $1 trillion opportunity in the market. This is the modern data stack. We won't have time to drill down specifically, but think of Snowflake at the center there as a cloud data platform. And there's some tenets of the modern data stack. It's actually a movement. You can search online. You can go to datastack.xyz. You can search modern data stack. You'll have no shortage of opinions of what it should look like and what the current state of it is, but there is some consensus. To be part of the modern data stack, truly a native part of the modern data stack, you need to be cloud native, you need to be relational, and be able to speak SQL. And among other things, you need to have a focus on automation and operations, right? The modern data stack was built to handle the high volume of data that we had talked about before, but there's a challenge. And the challenge is, have all these systems of record in the lower left-hand side, and these systems of record are siloed, they're application specific, they all have their own logic. And we as an industry have looked at this historically, and we said, okay, we have these different systems of record that have their own data and their own logic. Let's take the data and put it in a central store where we can then use it. But we've orphaned the knowledge, right? So we brought the data along, and the data is relatively inert, but you can do some things with it. But the challenge that we see, and the dawning realization on the whole modern data stack movement, is that when you do this, sort of compound the knowledge silo problem, right? So to pick a supply chain example, let's say you're a buyer and your boss says, listen, I want to understand why this category is struggling. What is going on with our profitability? And you want to look at a dashboard. In order to create that dashboard, you need to have some measure of cost, and maybe you have a notion of category landed cost. And you have the components for that, and it's, maybe it's your product cost, spoilage, less, customs, taxes, whatever it is. It's knowledge that's stored in the source system of record. But you didn't bring that over with you when you brought the data, and so now you have to specify what that knowledge is. How do I calculate landed cost? And you do it, whatever language you're using in your BI tool, maybe you're using Looker or LookML or Tableau. And you find that, I ran this report, and it does look like our landed cost is up and our profits are getting squeezed, and a big part of that is because we have the rate of spoilage is higher than it should be, and it looks like it's consistently that way. And your boss says, great, so what would happen if we just cut that vendor out? And forecast what would happen if we remove that vendor from our ecosystem. And so now you're into a forecast, and you grab a data scientist, and they grab a notebook, and they start writing something in Python, and you now have to teach Python how to calculate landed cost. So you've now duplicated the same algorithm that you specified in the BI tool that already sits in the system of record, and this plays out, over and over again. Maybe you're building a data app that uses mathematical optimization, and you want to not only put a constraint in that says, I don't want this vendor, but you want some other constraint saying, I don't want these types of items commingled, or I want to optimize for the best mix of contract versus market pricing, right? And again, let's say I'm writing that in Java, and I'm passing it off to a solver like Groby or Cplex. I've now specified in Java the exact same knowledge that I've specified over and over again, right? And so this plays out, and you have these bits of knowledge repeated throughout the data stack, and you're sort of breaking the tenets of the modern data stack. Things should be cloud native, and they should be relational. You don't want to leave that cloud native and relational cloud data platform, but you kind of have to for workloads that aren't supported. Right? So you end up writing things in these procedural languages or other languages and other platforms. And this is where we see an opportunity, right? We think our relational knowledge graph, and I'll see an example of that here soon, is well suited to express that knowledge in the cloud data platform itself, push that knowledge back down to a central repository where then you can much more quickly and efficiently and easily build intelligent data applications. By intelligent, I mean you're infusing them with capabilities like mathematical optimization or graph analytics or reasoning or certain types of machine learning, relational machine learning, graph neural nets, and so forth. So we are well positioned to help play this role. We see ourselves as sort of a natural complement to these cloud providers that are sitting at the center of the modern data stack. And by the way, I borrowed this diagram from DBT's site. I encourage you to put the links in here. You can go read about it. DBT and others in the modern data stack, there's this growing awareness that they need what they're calling a semantic layer, what we would just call a knowledge layer, right? You need a consistent way to view your data holistically, stitch these data together, specify how the concepts relate to each other, then push knowledge into that and automate the approach and the reasoning. And our knowledge graph, I think, is very well suited to do that. So quickly, a knowledge graph is essentially a database that allows you to organize data in a graph as concepts and the relationships between those concepts, where knowledge is represented explicitly. So knowledge, for example, might be something like, here's how you calculate landed cost. And in most of the world today, in most enterprise systems, that knowledge is currently stored in procedural languages like Java or what have you. Our take on this, to put a finer point on it, is we are going to take a relational approach to this, use all the advances in relational and cloud-native technology, plus our algorithms. We're going to organize the data as concepts and relationships. We're going to do it with a special data structure form, and we're going to that we can run our algorithms over that. We have algorithms that join these relations in very fast and very efficient ways. In some cases, counterintuitively, the more things you join, the more things you're looking to join, the faster it will go. And then we're going to represent knowledge explicitly in an expressive relational language, like SQL or like our own REL, which you'll see here in a minute. Jordan come up here. So, we think we're well paired. Our centers of these modern data stacks are these cloud databases that are relational. They're cloud native. We pair very well with them, and we handle workloads that they don't handle, like reasoning and graph and probabilistic and optimization workloads. So that was a whirlwind tour, and I hope I've just baptized your minds with what a knowledge graph and a relational knowledge graph can be. We had planned to get into some use cases, but I think I'm just going to turn it over to my colleagues here. I will say that there are use cases, like I mentioned the UN up front, where our clients are getting a lot of value. So we're not even GA, right? We'll be generally available sometime in early 2023, but we already have enterprise clients that are already paying to use, the meters running, they're paying service, and they're seeing a lot of value. And when we ask them, what are the benefits that you're getting? There's some variation, but there's a couple things that we hear over and over. One is over and over, regardless of whether we're working with data science teams or whether we're working with software engineering teams, the ability to weave together, to stitch together disparate data sources through a holistic lens, and then push knowledge closer to that data so that you can automate something, right? So I'm abstracting over, 4 or 5 bits of client feedback there, but I think with Kurt and Jordan, they can come up and maybe make that real for you, right? So Jordan has a background in supply chain, and you'll get, I think, a kick out of his stories here. He has a lived experience of the frustrations of having a swivel seat across a bunch of different systems when things go sideways. Kurt has a lot of experience building and implementing these supply chain systems. So I'll turn it over to you guys. Kurt.
All right, thanks, John. All right, thank you. And I want to pick up with a point that John ended on. He mentioned that there were a couple of good things about knowledge graphs. One is that they stitch together or weave together data from multiple siloed sources. And the other is that they directly encode knowledge. What I'm going to show you in the next few minutes is an example of how we do that and why that's, obviously, why that's beneficial in the context of a supply chain example. I think it'll be quite well. Okay? So let me begin here. The example I'm going to show to make this concrete is a supply chain that involves 3 siloed systems: a procurement system, a sales and ordering system, and a TMS, transportation management system, right? And what I'm going to show you here, these diagrams, these are what we call conceptual models of these systems. Conceptual models are the language of knowledge graphs, the language of the concepts and relationships that a knowledge graph reasons about. So I'll introduce it quickly with some examples, and we'll see it running. This is a procurement system at a very high level. Okay, the concepts that you're seeing in the little rectangles. Okay, thank you. Yeah, I'm an ex-professor, so I'm used to walking around. I'll try to stick with them. The concepts that you see here that are in these rounded rectangles, these are things that you might see and be able to search on in a UI of, say, so things like purchase orders, line items, items that are on a line of a purchase order, DCs that you ship to. So the relationships, what links these things together, are what we're seeing as these little connectors between them, right? So, for example, a PO line item is part of a purchase order, which comprises that PO line item, right? A purchase order is filled by a vendor, etc. Okay. So that's my procurement system. I've got a few concepts, a few relationships, and there's some data underneath this that I'm going to need to use when I'm doing any kind of work to reason about my supply chain. I've also got this sales system, sales and ordering system, which is another siloed system. This is allowing me, from the perspective of a store, for example, to be able to make orders, replenishment orders. Store orders are very similar to purchase orders that you send to a vendor in the sense that they have line items that are requesting some quantities of items. Okay? Very simplified again, but it gives us a separate system. You will notice, however, that there is some commonality, right? The sales system and the procurement system are both talking about quantities of items, right? So in theory, you might want to bridge these together and link them, for some reasons. Another more complex one here. I'm actually very proud of this because this is one that I built for a large bookseller a few years ago, and it's still in production. This does optimization. It's a transportation management system that does optimization of inbound traffic from vendors to DCs to try to minimize transportation costs. And I won't go into all the details of what it does, but it's got a very interesting structure to it. It talks about things like, all right, I've got inbound cases from a vendor, cases of items that I'm getting from a vendor in a DC that I'm going to put up on racks and pick from. Got these outbound cases that are the results of picking for a particular store that I'm going to ship. I've got these shipments, right? Shipments have arrival times, shipment times, and estimated arrival times, and all the like. Okay? You get the idea. Right? Here again, another system, separate from the first two. It's another silo. Right? But obviously, if I want to reason about my supply chain, I'm going to need to be able to interlink these things in a very natural way. Otherwise, we'll have some problems that Jordan's going to get to. Right? Now, the upshot of this is these three systems, you can see them as one big knowledge graph. Right? This is the way you should picture a knowledge graph in your head. A knowledge graph is a linking of the concepts and relationships of many different source systems, right? So that you can navigate among them without having to get out of one system. And what I want to show you is a little example, a real example of how a real knowledge graph that I've actually built for this, based on this model will work. So I'm going to hop out of presentation mode for just a moment. I'm going to take you to the need to switch tabs. This is in the way. There we go. Okay. All right. I'm taking you now to what we call the console that we use for accessing a knowledge graph and RelationalAI, our system. And what I have here is the ability to pose queries. Now, some background. That conceptual model I showed a moment ago, right, that defines the structure of my knowledge graph, I have already loaded that into a knowledge graph that we built out on the cloud. And I'm going to now query it and kind of show you how to access it and give you a sense of what you can do. So one thing we might want to do, for example, we might just want to say, all right, let me just see what are my items, okay? So I'll say, you don't really have to pay too much attention to the syntax of this. This is a little query language that we write. Typically, what I'm going to type here, you would actually access from a user interface. Someone like Jordan probably would not type this, but actually have a user interface that generates these kind of queries I'm going to show. But I want to show you the details of how it works so you can get some spots in it. Okay. So I might just, for example, say, let me see the population of the items, the item concept in this knowledge graph. You see there are things like chicken thighs and ground beef, strawberries, T-bone steaks. Right? These are the kinds of items that imagine that your restaurant, you got a series of restaurants that are shipping data. I might also ask, right, so those are the items. What are the distribution centers? Okay. This will tell me the distribution centers. What are the purchase orders that I might want to look at? Okay. And here they are. They've got these internally generated names and numbers, and I can really have to care about them. The data are all there. Okay. Now that's great. So we've got things like purchase orders and distribution centers and the like. They're all in our knowledge graph, but how do they relate to one another and how do we take advantage of that? Well, so you can also look at relationships. Remember that I said there were concepts of relationships in those models. Let me show you how you see a relationship. There's one called purchase order vendor, okay, which connects purchase orders to the vendors that the PO is submitted to. And you can see I'm relating now purchase orders to vendors. Right? I might also ask, can I go from purchase order or from a PO line item to the items that are on that line item? Okay, right. Easy enough, right? I'm just basically showing you data, but you get the idea. You can actually, using this query out, concepts no matter what data silo they live in, and relationships that are modeled no matter what they live. And that's not all that powerful yet, other than it loaded everything. One thing that makes it more powerful is, let's say I actually want to link together some data that are not directly related. As an example, let me just pop back over here real fast. Let's say I wanted to, in my purchase order here, I want to maybe I want purchase orders. I want to see what items total list of items that are on a purchase order, okay, no matter how they're broken down into lines. I don't have a relationship between purchase order and item, but I do have relationships from purchase order to PO line item and PO line item to items. What I can do then is I can pop back over here and I can do something slightly different. It'll be a little more text. What I can say is I want to now see an indirect relationship, which I write like this. Pop down here. I'm going to say that I want to report on a new relationship that I'm just defining right now in front of you. Okay, that's going to relate order and purchase order Let me just make sure. O in purchase order, and I in item. Okay. The way I'm going to get there is I'm going to say I basically want every combination of purchase order and item for which there exists some line item, pure line item LI, that links to that item, and for that same line item, PO line item, that links to this order. Okay. A level of O. I can run this. And now we see the items that are on purchase orders. Okay, I've now connected things that were previously not connected. Now that's all in the purchase order system, so maybe that's not that impressive. But what if I actually go across the silos now? What if I want to go from instead of just going from the items, I want to go to the inbound cases that came from a vendor? I can do that too. I can basically change this to inbound case. Okay, and I can say PO line item case. Oops, sorry. Case, and same thing. And now I'll see the inbound cases that were packed by the TMS to send this from a vendor to the DC. But hopefully you get the idea, right? I can connect these things very flexibly. It doesn't matter how long these paths are. I can just keep chaining this along, and I'm saying it very declaratively. I'm basically just saying how to literally connect the dots in that graph. Okay. All right. So that gives you a sense now of how we can actually access data in a knowledge graph. I want to switch back now that you have a sense of what a knowledge graph is, and that it can be accessed, and at least at a high level, the virtue of stitching together these data so that you can manipulate them. I'm going to hand it to my colleague Jordan to tell you a little bit about the kinds of issues he found, kinds of problems he had to deal with on a daily basis, and then I'm going to come back and show you how we fix it, how we help us sort that. Okay?
Thank you, Kurt. Not a doctor, so no coding from me. I worked in the supply chain industry literally my entire life. My dad is a 40, 50 plus year veteran. I grew up in the logistics industry. I worked in it before I got into data and analytics, and I've been an inbound logistics manager. I've been a strategic account manager. I've been a purchaser or a buyer at a food service distribution company in Chicago. So that's where a lot of this personal experience comes from. Is my last job, I managed 9 categories. And so I'll just give you a little glimpse of what my day was working in these disparate systems that Kurt has been referencing. So this is just the first few hours of my morning. I get in, first thing I do is I print out a paper report of what was sold last night. How does that affect my current inventory? Did we oversell on anything? Is there anything that I need to go place an order for and pick up locally to make sure that the stores that order from us get all of the product that they ordered because we oversold? Now that might mean my forecasts were off, or that might mean that we got more orders than we expected. There was a quality issue, something like that. So I have to figure out how I'm going to get these things, and that means that I have to get external data sources. So that would be by phone, fax order sheets, and we're not talking like 15 years ago. We're talking 5 years ago. I still had people faxing me orders. If I was lucky, I got structured data in the form of an Excel spreadsheet, or maybe they had a website. If I was lucky. So I had to know that, and I also knew that if I buy these things locally, it increases our cost by 10 to 30%. So every time I'm short, I'm cutting my own profitability, and my boss was not happy about that. And so once I'm done covering all my shorts, then I have to go start managing all 9 categories that I manage, which means that I had to start on the East Coast and then work my way west. And I would have to pull information from our sales system. I would have to pull information from external data sources like USDA pricing models. I would have to pull from our TMS system. And I would take all of these external data sources and merge them with our internal data sources via Excel macros that I had built. And that put me way ahead of my peers because I was the guy who could write Excel. So I built my own models in Excel in order to be able to some of these exogenous data sources and some of the internal data sources that weren't already connected. And it meant that I had to literally pivot between different things. I had to actually fight with my boss about getting me a second monitor because I was going back and forth between so many things. I ended up buying my own monitor because I wanted 2 monitors so that I could speed up the time that it took me to go back and forth between these different data systems, printing out reports, merging data, and actually doing it all electronically, which was a very, very big thing. They wanted me still to do it pen and paper. Like literally print it out and go line by line, pen and paper. That's how they wanted me to do it when I first started. So that was a lot of pain. And that was just the first few hours of my day on a good day. That was if everything went well. I can tell you, as we talked, as they mentioned earlier, there's a lot of volatility in the supply chain. There is never a normal day. I worked 9 to 10 hours a day, 6 days a week, slept with my cell phone by my bed. I was always on call because it was perishable produce, and if you didn't answer the phone, that meant your product might not get there on time. It might not be worth anything when it shows up. Very important. So you had to be very responsive. You had to be reactive to all of these situations. And my job was to be the knowledge graph. That was my job. I had to integrate these different data sources and respond reactively with the knowledge that I had acquired over 20, 30 years of either being around it or actually being in this professionally. So then you start getting into the nightmare scenarios. And let me tell you, when you get a notification that, hey, all of your inbound bag salad from your vendor in California has a listeria outbreak. The USDA says you need to now go find every bag of spinach that you have purchased that is potentially going to get sick. It is a holy crap moment, and you are very, very stressed out, and it requires that you do a lot of things, tracing everything back through your supply chain, and if you can't do that, you have to throw away all of your spinach. So that can be the difference between throwing away $6,000 worth of product or $60,000 worth of product. So the ability to actually be able to trace these things is super important. And I would have to spend hours going to these different systems and trying to trace back, okay, when did I place this order? Did I get the affected lots? Which stores did they go to? Is anything on a truck? Is it on its way to me? Is it on its way to a store? Is it already in a store? Has it already been served? It was a lot. So very stressful, very high-paced, and a system that can actually integrate these things quickly would have really, really helped me. It would have saved me a ton of time, maybe a little bit of stress, maybe had a little more hair. But Kurt, can you show us how we could actually do that in our system?
Sure. Let's take that that example with the listeria outbreak on spinach, right? And we find that out. Maybe Jordan gets a call at 6 in the morning before he's actually out. Says, hey, we just learned that this particular vendor was Reese's Orchard. Right, that their bag spinach has a problem. So anything from Reese's Orchard between these times, you need to now find, you need to take care of. So the way we go about this is a USDA recall. The way we think about responding to it in an analogy, I'll explain kind of what Jordan did and how we're going to automate it, and I'll show you the example. We actually think about this. So to track items at various points in the chain after recall, we know we need to trace what's being called all the way down possibly to the store. Racks on a DC, on trucks, things that have already been packaged. There are a lot of places you have to look. There's a lot of knowledge that someone like Jordan would use to figure out where could this inventory possibly be. Okay? So Jordan mentioned he would consult the procurement, TMS, sales systems, etc. So using a knowledge graph, what we're going to do, and what I'll show you in a moment, is how we can directly encode the knowledge that Jordan would use to find, track this inventory in these various systems so that we can automate it. I'll show you being automated. Now, to make this a quick example, I'm going to just kind of remind you from, if you think about if I'm tracing from an item that comes from some vendor, okay, all the way through the supply chain, there's a nice little choke point we can take advantage of, in the sense that there must have been a PO and a line item on a PO, maybe multiple POs, multiple line items, which those that product came from that vendor in that data range, right? So what I'm going to do is I'm going to show you how we can actually quickly say what are those PO line items. And once we've said that, that's the part that's going to be specific to the particular USDA recall, right? Spinach coming from Reese's Orchards on a date range. I'm going to show you how we can then automate the checking and tracking of all that inventory throughout the supply chain. Okay? Now let me quickly jump back into my handy dandy console. Right? Yeah. In the console. I'll get rid of this. And I'm going to cheat a little bit, so I don't have to do quite so much typing. I have this example up here. I don't want you to read every line of code, but I want to run it and show you what it does, and then talk you through the very first part. So let's run this. This is, take my word for it for the moment. This is the tracing that I just ran of this USDA recall, okay, which is for items coming from this vendor called Reese's Orchards, okay, where the item is bags of pre-washed spinach, right, that were shipped, or that were ordered, in a time interval between February 1st, 2022 and April 1st, 2022, right? This is the kind of information Jordan would start with, and now he'd have to configure it. All right, now that I know this, how do I find where all this stuff is? What you're seeing below here is the result of us having directly encoded, I'll show you in a moment, having directly encoded the kind of knowledge that Jordan used, and then we can execute that automatically to get this nice report here that blows it out by kind of phase in the supply chain, right? It's some of it we see, I'll just verbalize this for you. Some of this has been packed, okay? And it's at the DC in Dallas, and it's in a case with a serial number out case 004. Right? You can tell you that's where it is. And by the way, that's 30 units of those bags are in that case sitting in Dallas, waiting to go out. Some of them are actually outbound, okay? There actually is a shipment that, or maybe multiple shipments outbound from Dallas, going to store 287. There's 60 units there. There are in two different DCs, Atlanta and Dallas. Okay, I've got 90 and 510 bags of the stuff sitting on the racks, et cetera. Right. This is coming in from the vendor. It's inbound, and then some of it's already at the store. Now, you see the punchline, right? But being able to break it out like this, we can trace exactly where this inventory is. Okay, literally just by writing this. And you know, we can argue, I'm sure you wouldn't want to write this the first time because you're not familiar with the language, but you can imagine, I think you could read it, right? This first line here says that I'm interested in line items, LI, okay, that map to a vendor that is the vendor Reese's Orchards. The second one says I'm interested in items from line item LI where the items have pre-washed spinach. It's just a data. Okay. If I had a UI, you know, in a fancy graphical tool, it would generate this from things that I think are pretty obvious. Yeah, make sense? Now, let me briefly show you. I can't drill into all the details because there are a few cases, but I do want to show you how we encoded the logic, okay, or how we encoded the knowledge. This is, and I'll just do one of them, and then you'll see that the rest of them are the same. This is a rule. Okay, this is the kind of knowledge that we can put inside the knowledge graph. We frame them as rules. This one is framing a rule for deciding the quantity of items that are inbound, okay, from a vendor to a DC. Okay, given that we have populated this USDA recall of those line items. And just briefly, if I know that a line item LI was under USDA recall, I can map it to the DC, okay, using this little connection in my knowledge graph from a PO line item to a DC. I can see what case it's in, what inbound case it's in, right? I already kind of showed you an example of that, I think, the first time I was up. I know that the inbound case has shipped, but it has not yet been delivered. Okay, that's what tells me it's inbound. It's the kind of thing that Jordan would know. He would call it, has it shipped, then he would call it, he sees it as it. Right? Here we have all the data together, and we can just declare it and we say it, and now we've got it. I've got a different case, I've got a different rule for inbound versus on the racks versus packed, etc. It was by virtue of declaring this knowledge at once, all right, putting it in our knowledge graph, that we are then able to run this query at the time we need it at 6 a.m. You know, on a Wednesday morning or Thursday morning, and hopefully that gives you a sense then of at least this part. Yeah, I'll hand it back to Jordan.
Well, if you can pull back to the console real quick there, if you don't mind.
How much time would that query have saved?
Hours, and that is a great question. And I was actually going to say, you know what the most valuable commodity in business is time. And so if you can save people time, you can save people a ton of money. But the other piece here is also when we're talking about a recall of something that could potentially kill someone, time is also keeping that corrupted product off of someone's plate, out of someone's fridge, out of someone's mouth, right? So the way I would take this information is I would say, okay, first we have to start with the 10 cases that are at a store and make sure those don't get sold. Then we have to see which ones are on a truck on the way to a store and make sure those don't get delivered. Anything else that's inbound or in our DCs, that's lower priority because we are still in possession, right? But everything that's not in our possession is something that could potentially get to a consumer. And so this gives me a way to action this much, much quicker. And that's incredibly important when we're talking about a serious scenario like this, right? A serious recall, right? That's a really important thing to understand. And it would have saved me hours and hours and hours, which would have allowed me to respond more quickly, right? So, and you've got kind of all of the various logic here and the knowledge that Kurt has captured. That knowledge was codified into the code. Before it wasn't captured anywhere, right? And so another less serious example is, oh my gosh, you want to take some time off. Let's say your wife is having a baby, and you want to take a day off. Well, then you have to hand off your buys to a junior buyer who doesn't quite understand that there are certain items that can't ship together because one of them might be ethylene sensitive and the other one might be ethylene producing. And you get a truckload that shows up on your dock and everything is garbage. There's $130,000 down the drain because I took a day of PTO because my wife had a baby. So Kurt can show you how we can also handle something like this where we can set up integrity constraints and rules to stop spoilage and prevent spoilage from happening.
Thanks, Jordan. So this one I'm going to have to go through pretty quickly just in the interest of time. I'm going to switch back to the console here. This example was one where we're interested in when a shipment, okay, it's basically a constraint on shipments, right? That's what it wants, right? You don't want to put, you don't want to compose a truckload or an LTL where you have items that are producers of ethylene and consumers of ethylene on the same truckload. So what we do using a knowledge graph is we basically model what it means to be for an item to be a producer of ethylene, what it means for an item to be a consumer of ethylene, and then we first we'll write a little rule that will determine if any shipments that have already been created actually violate that constraint, right? That they have both items on there. And again, because we're running out of time, rather than do this from scratch, I'm going to show you the finished product of the code store. And we take this, pop over here, all right? And what I've done here, these first couple of lines are what I just said a moment ago. I'm going to basically declare knowledge that says what it means for some item I to be a producer of ethylene. In this case, it's simple. I'm just assuming that strawberries are producers of ethylene. I'm going to put okay, but it can be more complicated. Likewise, for items that are sensitive to ethylene, okay, I know pre-washed spinach is sensitive to ethylene. I think bananas are too. There are a number of different things. I would just list them all. Okay. Then I can basically do something like this. I can declare what it means to have an ethylene warning on a shipment. Okay. So this is a bit of knowledge I'm writing here that says some shipment S is just going to range over shipments. I'm going to give it an ethylene warning. Okay. If there exists two items, X and Y, right, where the shipment S contains both items, that's what these two lines are saying, right? Shipment S contains X and shipment S contains Y. Okay, X produces ethylene and Y is sensitive to ethylene. Anytime that happens, I'm going to now have a warning generated on the shipment. Okay, and you can imagine having a UI pop up whenever this happens and give some warning to the buyer to say, hey, go fix this. I also have one for shipments being late. Okay, because if they're more than 3 days, another kind of warning you might have is if a shipment's more than 3 days late, it's likely that you have spoilage. So you might want to generate a warning there. I can then basically now do this. I'll put this shipment warning. Okay. So it'll produce these, and it'll basically break them out by category too. Right, so there's an ethylene warning and a late warning. These are shipment IDs, so they won't make much sense to you, right? But they make perfect sense to someone who then has to go track it down and see, what trucks it is. Okay, so hope you get the idea there. Now there's one other quick thing, if I may, I'd like to say, because you mentioned early on supply chain optimization. Remember I mentioned at the beginning that one of the systems we built in the past was a TMS that managed inbound inventory into a DC. Using optimization, using a Gurobi solver, where you specify the constraints and you're trying to minimize the cost of fuel, basically, pickups, trying to optimize packing things on the trucks. We didn't yet at the time that we built that system work on outbound from DC to store. Okay, but that was next on our docket before I left to join this nice little company. The way you would express that is through something called an integrity constraint. Let me show you what that looks like, just briefly. Integrity constraint, here's a constraint that says your shipments have to be fresh. Okay, and if I put this in here, okay, I say, this is basically requiring that any shipment, okay, must be fresh, meaning that it doesn't have an ethylene warning. Okay, this basically says if S is a shipment and this is its ID so that I can report it and I can look it up, that implies that there is no ethylene warning on S. This is an integrity constraint, meaning it always must hold. If it ever doesn't, I'm not going to be able to take action in the knowledge graph. So here's, if I execute this, you'll see that I get a, when it runs, you'll see I'm going to get a constraint violation. A constraint violation tells me, constraint was violated, and here's the violator. Okay, down at the bottom, the fresh shipment. These constraints are useful for finding things after the fact, like what Jordan mentioned. But you can also use them as inputs to an optimization solver so that we would never ever generate shipments that would violate. And I'll hold that for another, maybe another topic, another presentation of this topic. All right. Nice.
All right, well, on behalf of the good folks at RelationalAI and Brennan Pursell and myself, John Bloys, thank you everybody for attending. I don't know how we're doing on time here. I think we're right on time, Brennan.
Yeah, we're about on time, but if there's questions, if people online have questions, you can just send them in the chat. If there are questions here from anyone, please at any time. I just think what's so exciting about this is, let's not get into debate about relational knowledge graphs are AI or not. It's a classic example of software and coding getting the data to work for the entity, right? And reducing risk, saving time, increasing efficiency, improving accuracy, reducing waste, and of course, boosting profits. It's exactly what this trend is going. And that was just really terrific. Let's give him a hand. Super. All right, please have some pie.
Now it's time for the pie in AI.
Yeah, right. Pie, coffee, have at it. I'll wind this up. Right, and for those of you who are still on the call, apologies for the delay in the Zoom call. With the Zoom credential, I've emailed all of you the URL of the full recording, so if you missed anything at the beginning, all right, so sorry about that stuff.
Knowledge graphs?
Yeah.
I joined the company, so there